Hello community, today we're gonna code FLAX. FLAX, as you know, is based on top of JAX, a specific library only for neural networks. Here we build our neural network system that we know, that we love, and we're gonna start with the easiest example that you can imagine. If you wanna follow along, here is the Google Colab for you. This is my notebook that I use. I just modified a little bit. So FLAX is an open source Python neural network library built on top of JAX. And we use here the simplest example that we have done 10,000 times in our career, a convolutional neural network. And we build it with a specific API. And this API is called Linen. Linen is a development that is too complex to explain, but we have it now, and we use Linen as the FLAX module system. And we can build our networks. So what we do in this video is we train here a network for image classification on the classical MNIST dataset. So beautiful. First we have to install FLAX. If you do a pip install FLAX, you have to know that you install only the CPU version. If you want to install, of course, here the latest version, you have here this beautiful command. And if you want to install some additional dependencies like matplotlib and whatever, you can go for install FLAX all. Let's try this one, because this will be the simplest FLAX you will ever see in your life. If you have a hardware configuration that has multiple GPUs and multiple TPUs, you go here, Google FLAX quick install, and you will see, yes, beautiful, that for multi-GPU, you have to configure your system for an optimal JAX FLAX experience. So here we go. Loading data. There's nothing specific in FLAX to load the data. So we have the beauty that we can use either PyTorch 2 or TensorFlow 2 to use our classical old-fashioned TensorFlow dataset. Input pipelines are data pipelines. And as you can see, I go here with Dataflow datasets. And we just here create here a training dataset and a test dataset from the MNIST dataset. So this is just to warm up that you wake up here for this video. And now we define our network in FLAX. FLAX, if you want to compare it to general relativity or to special relativity by Albert Einstein, go and study Einstein, because FLAX is really non-trivial. FLAX is really for the research community to train artificial intelligence systems on all kind, extremely fast on distributed hardware infrastructure. So if you're a newcomer, look somewhere else. This is not the FLAX you are looking for. So at first, we create now our first convolutional neural network with the Linen API by subclassing a FLAX module. This is easy. We will use here something I show you in a second. No, let's do it right now. We have here from FLAX import Linen. And please remember this NN that we have here for a traditional version is Linen. Whenever you think about NN starting today, you think about Linen. So we have here a class of our CNN, a subclass of our Linen module, and we build a simple convolutional neural network system. What you know is we have here our call function, and you have here layer by layer by layer by layer with different activations function, nonlinear activations function. And you build here your architecture of your neural network. And then you have here a beautiful compact wrapper that you wrap all your layers together. And I would highly recommend at the beginning you use this compact wrapper. Later on, I show you that there are more elegant and more powerful structures. So what I want you to remember, like in JAX, FLAX modules are Python data classes. Remember, data classes in my last video. Modules now in FLAX can contain submodules, a lot of submodules, and in this way they can be nested in a tree structure. So suddenly we have here the implementation again of tree structures. And you remember that in the video about the optimal data structure for JAX that I showed you pi tree data structures, which also have, what a coincidence, a tree structure. So you see in functional programming, you have now different to object-oriented programming here, that all your models have and your submodels have a nested tree structure of the submodels, and at the same time you have a pi tree data structure in JAX and in FLAX. And this will become very important if we go on distributed parallel training. So, you know now, Linen, our Linen API is just a module system in FLAX. Now, the next thing is nice, always visualize whatever you can. And here we have here this beautiful entabulate method, the command that you can apply on a module. And I highly recommend you visualize here in a table all the different module layer. So we just built this module, as you can see here, with all the subclasses. And here you have your inputs, your output, and your parameter. And you even have the size. I think this is a very nice visualization. Use those visualizations constantly. It helps a lot of if you want to do some debugging later on. Yes, we have a random key used to trigger the initialization functions. Those have default values provided by the module here. And initialization functions are called to generate the initial set of parameters that the model will use. You know this. What you may be not familiar with is a train state. What is a train state? Why we create a train state? Because it is elegant for the JAX FLAX transformation on distributed hardware. Now, a common pattern in FLAX is to create a single data class that represents the entire training state, including your step numbers, including your parameters, and most important of all, the complete optimizer state. And because we have this, and I will show you how we will use it in a distributed environment, we have here a special class, FLAX, training, TrainState, TrainState. And we will use this here in our simplest introduction example. If you want to have here the class definition here, you have here a step. The counter for the step starts at 0 and is, of course, incremented by every call to apply gradients. Then you have apply function. You notice the parameters to be updated by our optex gradients transformation and used by our apply function. Then we have tx, the optex gradient transformation itself, and the state of tx. So this is everything about the simplest version of train state. We will use this now. And of course, we install another library on top of FLAX. This is CLU. I will tell you about CLU in a second. Just think about it as another library that we use for some accuracy matrix calculation. So here we go. We have here, maybe I should execute here the modules. Otherwise, I just talk and I don't show you what we're doing here. So this is here we get our training data set, our test data set. Then we define here our module. Remember, I'm running here on the CPU only version. Beautiful. Train state, yeah, CLU, metric. Yeah, FLAX training import train state. This is a useful data class to have all the information about our train state. Then we have some specific data classes. Welcome to structure. Those are utilities for defining custom classes that can be used with or for JAX transformation. And if you are familiar with optex, great. If not, you remember we had FLAX or JAX optim. Now optex here is the new kit on the block for common loss function and optimizer. Beautiful. So we will be using CLU for computing metrics. For more information, there's the repo, there's a notebook. Beautiful. So what we have here for our metric, we have two factors. We have the accuracy, you know from neural network, and we have the loss function. Beautiful. The loss itself, sorry. So you then just go ahead a little bit. So you then subclass the TrainState so that it also contains the metrics for our evaluation, for example. This has the advantage that we only need to pass around a single argument to a function like TrainState to calculate the loss, update the parameter, and compute the metrics all at once. And this is beautiful if you do it on a distributed system. So you have here your metrics, and here you have now your function create TrainState. Beautiful. Create an initial, if you want, TrainState. Initialize the parameters by passing a template image. Yes, yes, yes. Here you have objects as you know it, as you like it. Beautiful. And what we do, we return a created TrainState, where we have our apply function, our parameters, our objects, and our empty metrics. Great. Now comes the most fun part. Maybe I should start the calculation for the rest of it. We'll be with you in a second. Yeah. So now comes the fun part, as I wanted to tell you, training. Now here comes most important step. This is now, remember, we are in functional programming, so everything is a function or a data tree. A function that evaluates the neural network given the parameters and a batch of input images with TrainState apply function, which contains the modular apply method, the forward pass as you know it, computes the gross entropy loss using the predefined objects, softmax gross entropy with integer labels. Beautiful. Note that this function expects integer labels, so there's no need to convert labels to one hard encoding. Beautiful. Because we only have the digits from 0 to 9 as our output classes. Then comes the beautiful part. The gradient of Jax evaluates the gradient of the loss function using Jax gradient and applies a pi tree of gradients to the optimizer to update the model's parameter. And if you have here now everything wrapped around a Jax JIT just-in-time decorator to trace the entire training step function and just-in-time compile it with our beautiful XLA compiler into a fuse divisor operation that runs faster and more efficient on a multitude of hardware accelerators. And you might say, oh, so this is it. A single training step that we have here, optimized for a distributed hardware infrastructure. So it is clear, we define here a function train for a single step. Then we define our loss function, our logits, our objects, softmax, gross entropy. Then you return the loss and you calculate your gradient. Beautiful. So next is that we calculate now the metric. So we create a separate function for loss and accuracy. We want to see how good is our system later on. Loss is calculated using the object softmax gross. Yeah, you know this. Interesting, here comes now CLU, our common loop utility that we have now for calculating the accuracy of our trained model. Therefore, we use here in the simplest example of all examples, CLU.metrics. If you want to learn more about common loop utilities and you have 5 to 10 hours that you want to invest in this, I highly recommend have a look at GitHub, Google, common loop utilities. And yes, of course, it was developed by Google. So then here we go. Define our compute metrics, our logits, our loss function, our metric updates, and we return the state. Yeah, as I told you, if you will see in some older programs, FLAX Optim, this has now been replaced by Optax, the new version. So please use Optax. If you want to learn about Optax, here, Optax, read the docs.io, latest Optax 101, recommended literature. Now, again, something simple, just download the data. My God, it doesn't get simpler than that. And as I told you, the seed randomness we take into account by random seed key. Beautiful. Yeah, next step, number 9, is to initialize the training state. So remember that the function, the create training state that I just showed you, initializes now the model parameters, the optimizer, and the matrix, and put them into a training state Python data class. Beautiful. So we just need some learning rate that we find. We have now a momentum that we can define. And then the command is easy, create training state for our convolutional neural network with a specific random key, with a defined learning rate and a defined momentum. Beautiful. Yeah, you can delete it if you have concern about memory. And then comes the beautiful step where you say train and evaluate now your CNN on the MNIST dataset. And we do this in JAX using the FLAX library to create our NNN architecture layer by layer. So at first, yeah, you create a shuffle dataset, you know this about dataset, but what I want to tell you here, define a training loop in FLAX. So you randomly sample batches from the datasets you have, you run an optimization step for each training batch, then you compute immediately after a mean training matrix across each batch in the epoch. So at first you have the training run, and then immediately you have the, if you want, evaluation run. Then you compute the matrix for the test set using the updated parameters, and it records the train and the test matrix for visualization. We will have here a very short matplotlib visualization. And once the training and testing is done, after I think I have 10 epochs, the output should show that your model was able to achieve approximately 99% accuracy. Remember, we're running here on a CPU only because this is the easiest configuration. If you have distributed hardware configuration, you will enjoy a lot more complex initializations. Okay. Since training DS is replicated num epochs time to get dataset, we divide it by the number of epochs. Beautiful. We set here our matrix more or less to 0. And then here now we have our training step. So for step and batch in enumerate our training dataset, we have here now the following steps. Run the optimization steps over the training batches and compute the batch matrix. So we have here our training step, and then we compute the matrix of it. So training step is clear, get updated training stat, which contains the updated parameters, aggregate the batch matrix, and after one step is, we do the following. The one training step has passed, we compute now the matrix, we record the matrix, and we reset the train matrix for the next training epoch, with the value, you're not gonna believe it, empty. And then, if we want to see how good our system is, we compute the matrix on the test dataset after each training epoch. So you notice this is nothing specific, and then there's just the print command that we can see exactly what we see now here on the screen. As I told you, we have the training epoch, and then we have immediately after the test epoch. So you see how good our system is performing. So, and as you can see, after 31 minutes, finally we have 10 epochs. So here we go. At first, let's have a look at the training epoch. So we have a loss of 0.007 and accuracy of 99.85%. And for the test dataset of our MNIST dataset, we have after 10 test epochs now a loss of 0.039 and an accuracy of 98.9. So very nice. Let's have a look at a short visualization in matplotlib. And these are exactly more or less the curve we expect. In blue, we have the training loss. And in orange, you can see here our test dataset. And the loss goes down more or less as we expected to do. Accuracy, on the other hand, of course, goes up, also the way we expected. So now that we have our train system, if you want, now comes the beautiful part, because now we can perform some inference here on our test dataset. So now define a jittered inference function. Now this is so nice, a jittered inference function, and the power is, as I showed you, this here was running on a CPU with only 2 cores. And you can run more or less the same program, the same code, on a multiple TPU tensor processing unit cluster in the cloud. This is so nice to have this possibility and optimized the fastest way possible to compute it. So how we do it, we define a jittered inference function. We predict here the step. We have here our state. We apply a function on it. And we have our test batch. And here we say predict step here on our test batch. Now let's do this. And at the same time, let's have a look at the result here. We just do some subplots of the numbers. Remember MNIST, so we show you here the label it should be and what as humans we would indicate here our little black and white images. And you see label 4, label 7, label 0, label 9, label 2, 6, 5 here. Yeah, okay, this is an interesting case. But you see, in general, our trained system behaves exactly as we wanted it to behave. So congratulations, you made it to the very first example of your JAX FLAX library example here, where we build a neural network with the professional if you want code. If you want to learn more about it with different Python modules, with different test models, there are a lot of other Colab Jupyter notebooks available for you in the FLAX Git repo. You have here GitHub, Google, FLAX, 3 main examples. And here, for example, MNIST, if you want this particular example. So if you want now to have a more complicated model, remember this was just a simple CNN model. Of course, you can go even and have you have layers then, where we have here instead of we have here dense. We have instead of a dense layer, you can have self-attention layers. You can build beautiful complex structures from transformers. And there's only that we do not call it transformers anymore. Than if we build it completely in FLAX, we will call it then a FLAX former. And those FLAX formers we will use for the T5 model training that we will apply on JAX and on FLAX. And for me, this was my entry that I wanted to run a T5 model and LLM model on a distributed hardware infrastructure with a professional code. So T5X, if you have a look at the GitHub repo, I will leave you a link in the description of this video. This is why we need to jump here through JAX and FLAX, because T5X has a speed improvement that is amazing if you compare it to the normal PyTorch 2 even, or the TensorFlow 2 version. So for the first interesting example here, where we define our network in FLAX, I hope you learned a little bit, you had a little bit of fun. This was a guided introduction to your first FLAX example here in the simplest code sequence possible. And I hope to see you on my next video.